All right, today we're going to talk about linearization differentials, kind of like we did with the previous section of related rates, where we're going to kind of talk about them the first day and then we'll really apply them the next. So, first thing I want to do is just kind of give a brief overview over what each one is. So, the big idea that works kind of for both of them is using the tangent line or the rate of change in place of the function. So linearization is an approximation of the function at a point with the tangent line. So basically what we're going to say is f of x is approximately, think back to our f prime of x naught and x minus x naught plus y naught, like that. So linearization is about approximating the function. And again, you have easy adjustments if there's for the factors that are nearby. And what that means is, like, if I'm going to estimate around 4, I probably don't want to stray too far from like 3.5 or 4.5, especially depending on how sensitive to change the function is. And the sensitivity to the change will come from our differentials. So think about, we have dy dx is f prime of x. What we're going to look at is the differential is this function, where you look at the derivative times the actual change in x, and that will give you the change in y. And this helps with checking, okay, maybe you look at stocks or ticket prices. If I were to increase the ticket price by $5, how much does that affect in the long run? Am I going to make more money? Am I going to make less money? And the sensitivity comes from how much more and how much less. Because if you're changing the ticket price from $25 to $30, the question is, does that affect how many people are going to go? Does it increase? Does it decrease? And more specifically, how much does it increase or decrease? So differentials are useful in measuring, are your changes going to drastically affect what you're actually getting out of it? So for example, with linearization, let's take y equals x squared, and we've got our tangent line here of 2x minus 1 at the point 1, 1. So if we zoom in, from about here to here, they look like they're about the same. Now again, they're not going to be exactly the same, but they look really close. Because again, the definition of a tangent line is it touches it at the point that you specified, and they share the same slope. That's the tangent line. But as you get closer and closer, the lines almost look like they lay on top of each other. So they look like they can just about be the same line if you're really zoomed in. Now, if you're going to estimate, like this one is zoomed in with only a 0.003 up and down, that's pretty extreme. But if you notice, once you zoom in that much, the tangent line is almost exactly the original function, which is going to be very useful. So our standard linear approximation is, if f is differentiable at a point A, which means f is continuous at that point, then the approximating function, L of x equals f of a plus f prime of a times x minus a, which is just our tangent line, which was y equals f prime of x naught times x minus x naught plus y naught, or some people wrote f of x naught, whichever, is the linearization of f at a, then the approximation f of x of, or is a, words are hard. The approximation of f by L is the standard linear approximation. And you call the point that you're approximating around the center of it, because everything is going to move either further away or in a positive or negative direction from that point. But the key takeaway is it gives you a decent approximation. It doesn't tell you exactly what the value is, but it tells you a very close approximation as to what the value is. So, key things: calculate your tangent line at the nearby point. And the reason I say nice point is don't pick a point that's going to be very difficult. If we're talking about squaring a number, don't pick 3.5. Pick 3 or pick 4. Just whichever way. You got to pick something that's going to work nice. Then you approximate that point with the tangent line. So maybe you're after 3.5, but you do your linearization about 4. Then you can use 4, or you can use an approximation about 4 to get close to what 3.5 is. To reemphasize, don't make it hard. Pick nice points. If you're dealing with trig functions, don't pick like 0.23. Pick pi over 4, pick pi over 2, pick stuff like that. That's going to be very close. And not only very close, but give you good values. So our first example, what's the linearization of f of x equals x cubed minus 3x at x equals 2? That's basically asking, what's the tangent line at x equals 2? So if we're going to do that, first thing I need, what's f prime of x? So power rule. So 3x squared minus 3. Now I also need what is f prime of 3. So that's going to be, f prime of 2. I wrote way too many 3's down. So f prime of 2 is going to be 12 minus 3, which is 9. But I also need f of 2, because we're using our tangent line. So 2 cubed is 8 minus 3 times 2. So 8 minus 6 is just 2. So this is what our tangent line will look like. And remember, we're calling it a linearization, so we don't write y equals, we say L of x equals. So L of x equals 9 times x minus 2 plus 2. And the 9 comes from here. The 2 in here comes from that 2. And then the plus 2 at the end is going to be the plus 2 at the end comes from finding what is f of 2. And then if we want to, which I would prefer, we have L of x is equal to 9x minus 18 plus 2. So that means our linearization function is 9x minus 16. So remember, this is our linearization centered at 2 for our given function, which is basically the same thing as saying, what's the tangent line at x equals 2? The only difference is instead of saying y equals, we say L of x equals. and we put it in kind of a different context. Now notice, let's see, here's 2. And let's see, we said at 2, we were at 2. So that means probably about here. When in doubt, just make the dot bigger so it hits every point you need it to. And you notice as we go up, it's actually not a bad estimation even as we get farther and farther up away from 2. So this one's holding pretty well. But as you go to the left, you're getting really, really bad estimations. Now, there's a possibility that at some point, as this goes down and down and down and down, it could intersect again. That could happen. And it might be a useful estimation one more time going to the left. As you can see, it's really only good not even quite to 1, so about 1.5 you're already starting to lose a decent amount of accuracy. Versus this one at 3, you might still actually be okay. So now this is one example. So what's 1.9 cubed minus 3 times 1.9? Basically, I'm asking what is f of 1.9? Now, 1.9 cubed, can we do that? Yeah. Do I want to do that? No. So, let's use our linearization because, remember what we said? F of the point is going to be approximately the linearization about the point. So, really all I need to do is do 9 times 1.9 and then subtract off 16. So 9 times 1.9 is going to be 17.2 or 17.1, sorry. And that's going to be minus 16. So that means our linearization at 1.9 is 1.1. So we know that f of 1.9 will be approximately 1.1. And so you can see there it is zoomed in, which here's 1.9, which goes to there. So it's really close, not quite exact, but we got the first decimal place right, so that's not too bad. And in the grand scheme of things, we just needed a decent estimation, so we're actually doing pretty good. So now what if I said what's the linearization of f of x equals sine squared x at x equals negative pi over 4? Again, same thing as just asking what's the tangent line at x equals negative pi over 4. So the derivative of sine squared, this is chain rule. And you got to think of u is sine of x. So this would be 2u times the derivative of sine of x is cosine of x. So this is going to be 2 sine x cosine x. So now I need, well, I'm going to need f of negative pi over 4, and I'm also going to need f prime of negative pi over 4. So let's start with f prime. So f prime of negative pi over 4 is going to be equal to 2 times sine of negative pi over 4 is going to be negative square root of 2 over 2 times cosine of pi over 4 is going to be positive square root of 2 over 2, which this is going to give us, one of these 2's would cancel, and then, so let me just multiply everything out. So this is going to be 2 times negative 2 over 4, which is just negative 1. So our slope is negative 1. And then if we do f of negative pi over 4, that's going to give me, well, we already found sine of pi over 4. So it's going to be negative square root of 2 over 2 squared, which is just positive 1/2, because we'd get 2 over 4, which would reduce. So that's what our graph looks like. So let's write our linearization. Our linearization is going to be negative 1 times x minus, technically it'd be minus a minus pi over 4, so that becomes plus. And then plus 1/2. So this one, not really super useful to try and expand it out, just because I'm not really going to get too far with it. But notice things actually do line up with the graph. We have a negative slope. Our slope is negative, and then at 1/2, which is here, that's where our tangent line touches. Again, my little dashed line is not very accurate because of my lack of artistic abilities, but moving on from that. So here's a case where, like I was talking about, when would it be useful? Sine of negative 0.75. One, you've already got a lot of estimation going on. There are no exact values in this case, so if you even calculate sine of negative 0.75, that's going to have rounding error. And then if you do sine of negative 0.75 times sine of negative 0.75, which is what's going to happen here, that's going to compound even more error. So this is our f of x. So like we did with the previous one, I know that f of negative 0.75 is going to be approximately my linearization about that point. So this is going to equal negative 1 times negative, and I don't want to do 0.75, so I'm just going to go ahead and convert it to negative 3/4 plus pi over 4, and then plus 1/2. So this is going to be negative 1 times negative 3 plus pi all over 4, plus, I'm going to go ahead and get this with a common denominator, so plus 2/4. So that's going to equal 3 minus pi plus 2 all over 4. So I'm going to get 5 minus pi divided by 4. Now, if you're saying, well, that's still got some estimation going on, you are correct. Pi is going to have to be estimated. But when you do computations, if you multiply something that's been rounded by something else that's been rounded, that's compounding that rounding error on just continuously. So in this case, when I do my calculation, 5 minus pi, that's a okay estimation. And then if I divide it by 4, wherever I stopped, that is going to influence how good or bad my estimation is. Don't use 3, maybe go out a few decimal places. It all depends on how accurate you need to be. Parts that go on rockets have a much tighter margin of error, as opposed to maybe you're just building a fence in the backyard. If you're off by a little bit on the fence in the backyard, no big deal. But if we're talking about parts that go on rockets or cars, or you're building a multi-story building, then probably need to be as accurate as you can. So if you were to put in a calculator sine of negative points or sine squared of negative 0.75, you get 0.4646. That's stopping at 4 decimal places. If you do the linearization of negative pi over 4, negative 0.75, we use negative pi over 4, you get the exact same decimal places and then a 2. So it's a really good estimation for this one. So a differential is kind of just taking what we know, because if you notice, this is just dy dx equals f prime of x. And I said, okay, well, what if I multiplied both sides by dx? Then you get the differential. The differential is an estimation of how much is changing at a given point from another point. So if you go back to your definition of a slope, which was rise over run, or we had delta y over delta x, which would equal y2 minus y1 over x2 minus x1. That bottom part in the denominator here, that's going to become vital because you need to know how far away you're moving from your given point. Because that dx is telling me that is a change in x. So if you go from 3 to 4, that's an increase of 2. So your dx there is 2. If you go from 3 to 2, you decrease by 1, so negative 1 is the dx. So you have to be very specific and very careful in those cases. Because basically, it's the rise equals the slope times the run. It tells you how much you've gone up by multiplying, or I should say how much you've gone up or down by multiplying the slope at the point times how far you've moved on the x values. And again, the context is your clue. Dy dx is the derivative of y with respect to x. That's our Leibniz notation. So dy dx is the limit of the change, because remember, if we go back to the formula nobody likes, we get the limit as h goes to 0 of f of x plus h minus f of x, all divided by h, is f prime of x. So what's happened is everything is this limit is telling you how much it's changing, and it gives you dy dx. Now it seems very, again, trivial. If I do dy, that equals dy dx times dx. Those should cancel. But we don't want to cancel them. And the reason for that is I'm more so leaning into the equation that's over here. Because I'm kind of approximating the change in y with the derivative at the point times how much did I move about from x, that point that I was plugging in. So, and you'll see kind of how they both play in the reason linearization differentials are paired together. So we'll do our first example. And the nice thing is, if you notice, it's very close to what we did before. In fact, I was very nice in this one, just went ahead and picked the problem we did before. If I'm asking what's the differential, I'm saying what's y prime dx. And remember y prime, this could also be f prime of x dx at x equals 2. So we already talked about our f prime of x is 3x squared minus 3. And f prime at 2 was 9. So my differential is 9 times dx. Key thing here, this is about x equals 2. Because dy equals f prime times dx, so dy is just the derivative at the point you're looking at times dx. The dx part we'll see in a moment. Because if you're looking at this going, okay, well, what do I do with the dx? Dx is fairly simple. What's y at x equals 1.9? Well, or sorry, what is dy at x equals 1.9? Notice this was what we centered our differential about. 1.9 you can think of as 2 minus 0.01. So this is our x2 minus x1. Almost. So what I have here is how far away did I move from this point 1.9? Well, from the point that I centered about, it was negative 0.1. So that means dy is going to equal 9 times negative 0.1. So that means dy is equal to negative 0.9. So that what that means is, just to write it out in words, so if I move, so basically what it says is if I move from f of 2 to f of 1.9, the change in y is negative 0.9. And that's based off of our differential. You could also test, well, what if I plug in f of 2 minus f of 1.9? You could do that as well, but the whole point of this is getting the change and staying close to it. Clearly, you don't want to try and check, well, what if I move from 2 to, I don't know, if you move from 2 to 0, that's a change of 2, or that's a decrease of 2. So that's going to have a drastic effect. But also, if I want to estimate the change over here, notice that I can't even map where this line is going at 0. So you probably, like beforehand, you don't want to stray too far from your given point. If you're going to check around 0, maybe go ahead and actually just evaluate y prime at 0, at x equals 0, and make that your new centering point. Don't pick a bad point for estimation. So like here, if I'm going to estimate probably between 1 and 3, I'm going to be okay. Even if you notice 1 is still kind of drastically off from there. But be wise about these. If you're going to use them for estimating rates of change, check close by. Don't check very far away. So if we go back to our trig example, what's the differential at x equals negative pi over 4? Same as asking what's y prime of x dx or f prime of x dx at x equals negative pi over 4. Well, we already found f prime of x is 2 times sine of x times cosine of x. So at 2, or not 2, let me be stupid for 3 seconds. At f prime of negative pi over 4, you get, what was it we said, negative 1. So dy is equal to negative 1 times dx, or just easily, I can't talk. dy equals negative dx. So there's a very interesting change here in that at dx, or at the change in y, if you start at negative pi over 4, is just going to be negative how far did you stray away from x. So if I say how much does sine squared x change if it goes from negative pi over 4 to negative 0.75, well, that's approximately a change of 0.035. So from that, we get dy is equal to just negative 0.035. Now, one thing you need to keep in mind is what would be a bad point to test a differential? Don't go for places where the derivative is 0. So for example, let's say I look at f prime of 0. It just happens to be 0 here. Or just to show that it's not just at 0, let's say I do f prime of pi over 2. Then I get 2 times 1 times 0. So that means dy is equal to 0 times dx. So the change in y is just 0. And it doesn't matter how far you go away from pi over 2, your estimation, because remember, dy is an estimation. If I go from pi over 2 to 0, it's still the rate of change is 0, but you can see if you're here and go to 0, there's a pretty drastic change. But because you pick a bad point, you're going to get a bad estimation. So be aware of that. So here's the cheat sheet for it. And by cheat sheet, I mean I'm just gathering everything in one place. So if y equals f of x, and you're given the points x naught and y naught, then your m value, or the slope, is going to be dy dx evaluated at x naught. Same thing as just having f prime of x naught. I can write an equal sign. I don't even need to do the little parentheses. So then your linearization, I don't know what that's, there we go. So L of x is equal to y naught plus m times x minus x naught. Your differential is dy dx times dx, which is just the slope, times the change in x. Now, if you do differential approximation, if you notice, that's just y naught plus dy dx times dx, which is basically still getting you right back to, because remember we said dx was basically kind of like an x2 minus x1, but in our case we have an x minus an x naught because we're keeping it generic. That's what it gets replaced with. Differential approximation is the is basically the same as linearization. Because if I say what's the differential approximation, you're still using, basically this is kind of like saying I'm doing y naught plus f prime of x naught times the change, which gets you again right back to just your linearization formula. So you basically are finding the same thing if it says linearization or differential approximation. Whoop. I apologize for the practice being scratched out for some reason, but those are just some good problems. And this is what I recommend starting with, just to kind of get the idea down for these linearization and differential problems. And then in the next one, we'll go through and we'll do some applications of them and maybe do a little bit more practice. So I'll see y'all next time.